Good day everyone. We are pleased to present our assignment on control charts for attributes under the subject Quality Assurance and Quality Control in Engineering Technology. This presentation is brought to you by Madhumita Kumaravel, Anastasia Ignatius and Durgashini Ilango. Our focus will be to explore the application of control charts in Quality Assurance QA and Quality Control QC. Let's get started. Here is an overview of what we will be covering today. First, we will discuss the difference between quality control QC and quality assurance QA. Next, we will explain how control charts for attributes fit into QA and QC processes. We will also explore the different type of control charts for attributes and their specific applications. Finally, we will dive into the principles of statistical process control and discuss the importance of control charts in identifying and correcting processes. Let's start with understanding the distinction between quality control and quality assurance. To begin, let's define QC and QA and see how they differ. Quality control is a reactive approach focused on detecting and addressing defects in finished products. This typically involves inspections, testings, and audits to ensure the product meets the required standards. On the other hand, quality assurance is a proactive approach aimed at preventing defects from occurring in the first place. This involves process design, risk management, and continuous improvement to build quality into a process. To summarize, QC is more about inspection, while QA emphasizes process improvement. Now, let's see how control charts for attributes integrate into these approaches. Let's talk about the control charts for attributes, which are a crucial tool in quality control. These charts help us to monitor the performance of a process by focusing the defects and defective items. On this slide, we can see the four types of control charts: the P chart, NP chart, C chart, and U chart. Let me walk you through their purposes and examples. First, the P chart is used to track the proportions of defective items in a sample. For example, it can measure the percentage of defective units in a batch. Next is the NP chart. It is officially for counting the numbers of defective units in a sample which are a constant size. For instance, the total defective items in a daily production run. Then we have C chart, which will monitor the count of defects in a fixed sample size. An example would be the number of defects per unit in a product. Finally, the U chart is for tracking defects per unit when the sample varies. For example, it measures the number of defects per unit in a shipment of differing quantities. Next, we are going to talk about how control charts fit into quality assurance. The purpose of control charts in QA is to ensure that processes are designed to prevent defects. By monitoring processes continuously, control charts help to identify variations that could lead to defects before they occur. The goal is to keep the process in a state where defects are minimized and ideally prevented altogether. In QA, the focus is on preventing defects by improving processes. Control charts help to track variation in processes and provide data to identify when corrective actions and improvements are needed before defects happen. They allow teams to monitor the effectiveness of the process and make adjustments proactively. Quality audits, process reviews, and continuous improvements are typical methods used in QA. Control charts provide valuable data that help to evaluate process performance, detect areas for improvements, and ensure the process remains capable of delivering quality results consistently. In practice, control charts in QA are used to assess process effectiveness. Where monitoring key data process, we can see if processes are stable and capable of consistently producing quality products or services. Next, to improve processes. Control charts allow teams to detect trends and variations early, providing an opportunity to make improvements to the process before defects occur. Next, we are going to see how control charts fit into quality control. The purpose of quality charts in QC is to monitor process variations and identify defects. Control charts track products' quality over time, helping to identify the process may be going out of control. The goal is to ensure that the final product meets the quality standards by identifying issues early and making necessary corrections. In QC, the focus is on identifying and correcting defects in a product services. By continuously monitoring product quality using control charts, teams can identify when products are not meeting specifications and take corrective actions. This helps to ensure the quality products reach customers. In QC, typically the methods that are used to inspect the control of the quality is by inspecting and testings, sampling and analysis, and corrective actions, where control charts track variations in product quality over time, helping to determine the process if it is stable or if the corrective actions are needed in the future or in the real time. Next, in practice, we can see the control charts in QC are used to track variations in product quality, where monitoring data like measurements or detect rates to ensure that the products consistently meet standards. And then we can see it also determines the process stability. If the data points fall outside of control limits, corrective actions are needed to bring the process back into control to prevent the further defects from occurring. I will next give my presentation to Anastasia Ignatius to continue with her part of the slides. Thank you.
Good morning, Dr. Rosniza. My name is Anastasia, and I am going to present about the types of control charts. So there are four types of control charts, which is the P chart, NP chart, C chart, and U chart. So let us look into what P chart is all about. So the purpose of a P chart is to monitor the proportion of defective items in a sample, and it can be defective or non-defective. It is classified under binary data type, and it is ideal for situations where each unit can be classified as defective or non-defective, such as tracking defective products in manufacturing. And the examples are, in real life examples are monitoring the proportion of defective parts in an automotive production line, such as identifying faulty brake pads, and monitoring the proportion of patients who experience post-surgical infections in a hospital. Next, we will look into NP chart. So the purpose of an NP chart is to track the count of defective items rather than proportions. And NP chart type is a whole number counts of defects, and it is widely used in tracking defect rates in manufactured items. So the real life examples would be tracking the number of defective syringes in a batch of 500 inspected units to ensure patient safety, and it is also used to monitor the number of improperly sterilized surgical tools in a set of 50 instruments checked daily. Now we will look into what C-chart is all about. So the purpose of a C-chart is to monitor the number of defects per unit in a sample, and C-chart is a data type, and the application is used when there is no predefined sample size, for example, counting defects on a single large sheet or surface. The real life example would be tracking the number of defects like scratches or dents on cars produced per day, counting the number of medication errors in a department during a shift, and counting the number of errors in process insurance claims per batch. Next, I'll be talking about U-chart. So the purpose of a U-chart is to monitor the average number of defects per unit, and U-chart is widely used when sample sizes vary. The real-life examples will be evaluating defects per unit in variable size sample, such as defects per square meter of fabric, and tracking the number of falls per patient day in hospital wards with different patient loads. And not only that, but it can also use to monitor error per pages in documentation review processes. This is a summary and comparison of all the charts that I have spoken earlier. Let us look into P chart. P chart is a binary data type, and it is used to monitor the proportion of defectives. For example, proportion of defectives light bulb. And NP chart, it is also a binary data type which is used to count defectives, like number of defective tires in a fixed sample. C chart, on the other hand, is a count data type. It is used to monitor the defect count, like number of errors in an invoice batch. Last but not least, the U chart is also a count data type, and it is used to monitor the defects per unit in variable size samples. And the real life example will be defects per square meter of fabric.
Good afternoon, everyone. Today I'll be discussing the principles of statistical process control, or SPC, and the importance of control charts in identifying and correcting processes issues. SPC is a key tool in ensuring that processes remain stable and deliver consistent quality. Throughout this presentation, I'll guide you through the basics of SPC, the role of control charts, and how they help improve efficiency in various industries. Okay, let's start by understanding what Statistical Process Control or SPC is. SPC is a methodology that uses statistical technique to monitor and control processes. The main goal of SPC is to ensure that the process remains stable and predictable by identifying variations before they lead to defects. Every process has some level of variability. SPC helps us distinguish between common cause variations, which are inherent to the process, and special cause variations such as abnormal and often require immediate attention. This proactive approach helps maintain quality and efficiency. Okay, why SPC is so important? There are several key benefits. First, it improves product quality by ensuring the process operates within acceptable limit. Second, it reduces process variability, which minimizes defects and rework. Third, SPC enables us to detect issues early, preventing costly waste and downtime. Ultimately, this improves customer satisfaction as the final product is more consistent and reliable. And as a bonus, SPC is cost effective in the long run because it reduces the need for extensive inspections and corrections. To understand SPC, we need to focus on a few core principles. First, we must recognize that variability is a natural part of any process. Common cause variations are expected and stable, while special cause variations indicate something is wrong and needs immediate investigation. SPC relies on tools like control charts, histograms, and Pareto charts to analyze data and identify trends. Finally, SPC supports continuous improvement, which aligns with broader quality management systems like total quality management. By applying SPC, we are not just solving problems but improving processes for the future. Now let's talk about control charts and why they are so important. A control chart is a simple yet powerful tool used in SPC to monitor process performance over time. It helps us to identify whether a process is stable or if it's being affected by special cause variations. Control charts allow us to track data, trends, detect deviations early, and make adjustments before defects occur. This reduces waste, improves efficiency, and ensures compliance with quality standards. Ultimately, control charts provides us with a clear, data-driven way to make decisions about our processes. Control charts are not just about monitoring, they also help us to identify issues. There are several signs that a process may be out of control. For example, if a data point falls outside the upper or lower limit controls, that's a red flag. Similarly, a run of 7 or more consecutive points above or below the center line could indicate a trend or shift in the process. Other patterns like sudden cycles or clusters also require attention. When we spot these signals, it's essential to investigate and address the root cause immediately to restore process stability. To summarize, statistical process control is a vital methodology for maintaining process stability and ensuring quality. Control charts play a key role in identifying variations, reducing waste, and improving efficiency. By integrating SPC into our operations, we can achieve consistent quality, meet customer expectation, and reduce costs. So I encourage you to explore how SPC can be applied to your processes and make it a part of your quality control strategy. Thank you.